Hi, everybody. Welcome back to Chem 140. Have to get rid of the music here. Hold on. I am not playing this off of YouTube this time because Final Fantasy V, the remaster, came out today. So instead of grading, which I'm almost done, I've been playing this all morning. Let's see here. I gotta get everything up in the front here now because all of my windows are everywhere to try and get this to work. So there we go. What do we got going on here? We have more Unit 12 today. We're going to finish this off just because it's relevant to lab worksheet number 4. But as far as things that are due are concerned, there is a quiz for Unit 6. Or not Unit 6, I'm sorry, it's quiz number 6 for Unit 11. It is due tonight. Make sure you get that in. It closes tomorrow. Don't want to not have that done. That's the naming quiz, by the way. Okay, so we've spent a lot of time talking about how to do calculations from atoms to moles and grams to moles, and now what we're going to do is we're going to put those things together in the context that you would see them in the laboratory. So, for instance, I go to the lab, and you go to the lab, presumably because it's lab day or whatever, and the instructions tell you, hey, weigh out enough to react with 1 mole of HCl or whatever. And so you have to weigh out whatever reagent it is. Like maybe you have an unknown and you only know that like its formula and its mass. I guess it wouldn't be unknown then. And you have to do the calculation. So what you'd have to do is turn grams into moles and then figure out how to calculate what would react with it. We're going to start doing the calculations that will lead up to that process today. And then in Unit 15 and 16, we're going to sort of finalize it and bring it all together. So let's talk a little bit about these types of calculations. In the previous lectures, we showed you, again, this sort of calculation. You're going to see this chart a lot because it's like a blueprint that guides you to do the calculations. If you're having trouble using your phone calculator, there's 2 things you could do. One is you could turn your phone sideways. If you do that, it turns it into scientific calculator mode. That may help you. But there are better options out there. Use Wolfram Alpha online. Let me get the link for that for you. If you aren't like near a computer, turning your phone sideways is probably the best cheap alternative. But not a lot of people know that. In fact, I didn't know that for the longest time. I use this website right here, Wolfram Alpha. You can type any calculation you want into that, and it will solve it for you. And we've been using that a few times throughout the quarter. Sorry, I gotta bring all my windows back up. There we go. So yeah, try that. Let me know if that works. Obviously, having a scientific calculator or like a TI 83. TI 83 is overkill. Don't spend $100 on the calculator. You could buy a TI 30 for like $20. Go to a dollar store. You'll probably get it for $1 or something like that. All right, so we talked about how to do particles to moles by using Avogadro's number. And remember that that number, again, is... Oh, I don't have the pen selected. Hold on. .022 times 10 to the 23 objects per mole. Now, yesterday we also talked about how you could turn grams into moles, and you use the periodic table for that. And if you have an element, you just take its atomic mass off the periodic table. And if you have a compound, you just add all of the atomic masses together to get the formula mass, also known as the molar mass. And so remember that this is for grams per mole. Now, the last thing that we did yesterday, we were talking about moles of something within a bigger molecule. That was this right here. So remember the P2O5 thing, where I said in 1 mole of P2O5, how many moles of phosphorus were there? Oops, sorry, 2 moles of phosphorus. And the reason for that is because that number just shows you right there. It's in the formula, right? Now, what does all of this mean for us? This means that if I know how much of some quantity I have, so maybe I have P2O5 over here, and I want to get moles of P, or not moles of P, but just phosphorus. If I know the number of moles of P2O5, I automatically know the number of grams and also the number of particles. Right? But using this connection, using these formula subscripts, I could then figure out the number of moles of phosphorus over here, which I could then convert to the number of particles of phosphorus or the number of grams of phosphorus. In other words, what I have is a sort of a bridge that connects a mass all the way through moles to another mass. And so I can convert masses indirectly through moles. So if I know how many grams of P2O5 I had, I could turn it into moles, then use the idea that there are 2 moles of phosphorus per mole of P2O5 to get the number of moles of phosphorus, and then turn it into grams. We have done all of these calculations individually so far. Today, our goal is to put them all together. And that looks like this. So here's just a fancy chart that you can use as a sort of blueprint to do all of these types of problems that you're going to see today. You're also going to see these types of problems in the laboratory. Commonly in the laboratory, you're going to do something like this. I'm going to give you a mass of something that I weighed out, because our balances weigh in grams, right? They don't weigh in moles. Moles are a counting unit, whereas grams are a mass unit. If I know the number of grams of anything, I can turn it into moles. And then if I know the number of moles of that thing, I can figure out the moles of any of its parts. And then once I've done that, I can do whatever I need to. So you may only want to know the number of moles. Maybe you're making a formula in which you would determine the number of moles, and we'll show that in Unit 13, as well as later today. Or maybe you want to figure out the amount of grams that you need to weigh out for a second reagent, or something like that. In any case, this is the gist of what you're going to be doing. You're going to be turning things into grams, from grams into moles of some subcomponent of that, and then into grams again. Maybe you need to turn it into particles too for some other application. Maybe you're just interested how many atoms are in this object you've made or whatever. And you can do that. But for the most part, this is going to be the process that we do, back and forth like this. If you've ever had Valerie, she calls this gamolmaga. Because that's where you're starting with, is you're starting with ga, and you're turning it into a mole, turning it into some other mole, and then ga again. So gamolmaga. I've sort of appropriated it from her because it's catchy. I cannot select this for some reason. Why is that? Why can I not click on you? There we go. Oh, I might have like something in the way of the tablet. Okay. Now, on this chart, every time you move from one box to another, you're going to do a conversion. So if I give you a number with grams, so like some number of grams, and I want to turn it into grams of another thing eventually, I have to move 3 spaces. So I'm going to turn this into moles first, and then I'll turn it into moles of something else, and then I'll turn that into grams of something else. So here's the first conversion, that's right here. Here's the second one, which is this process, and this is the third one. So each time you move, you're doing a conversion. We've been doing this all along, really, when I write out those little charts on the side. Like, oh, I want to turn from feet to centimeters to millimeters to whatever, right? Each time we moved from one unit to another, we had to do a conversion. Same thing here. So let's do some examples and you'll see this in action. Now, the real trick to these problems, and this first problem I've put in here is, it's a review problem. You've already done this problem. We did this yesterday. The reason I put this in here is so that we can, one, get used to the chart, and two, realize that the problems that we did yesterday will still exist. Even though we've introduced this process where it's like, oh, I can convert anything into anything I want to now. Sometimes you won't actually need to go on the right side of the diagram. Let me get a different color here. Yeah, so you may not need to actually use the B side of the diagram. Now, what is meant by A and B? A and B are just going to be things that you are looking at in the problem. So for this instance, I'm looking at vitamin C, which is this. So I'm just going to call that A. So whenever I refer to particles of A or moles of A or whatever, I'm actually referring to particles of vitamin C or moles of vitamin C or whatever. If I had a different problem where I had multiple things in there, so maybe I was looking at oxygen as well as vitamin C, and the question was like, how many atoms of oxygen are in this sample? Then I would assign B to be the other thing. And then it's up to you to look at the context of the problem to try and determine what exactly am I doing here. So for this problem, let me get rid of this because we're not actually using it. I'm only talking about vitamin C, and I give you a mass. Wow, it's being really picky today. I don't know why this isn't working. I'm going to give you a mass of vitamin C, and I want to know how many vitamin C molecules there are. In other words, I've given you this right here. This is where we're starting. Where on the chart do you want to go? Well, I want to use vitamin C molecules in my answer, so I want to go here. This is my goal. So your first objective for these types of problems is to identify where you are starting and where you are going. And so we've done that. Then what you need to do is do the conversions to set up the calculation. And so we're going to do that on this slide because I have space for it here. So, okay, let me change the color here, if it will let me. There we go. All right. So I have 0.250 grams, and I'm just going to abbreviate this vitamin C. And so my first step to get from the start to the goal is to go from grams to moles. So I'm going to write those units in here. So grams vitamin C, moles vitamin C. And those units would cancel out. And now if I hit enter on my calculator, after I filled in these numbers, of course, I would have moles of vitamin C. Then I want to move from moles of vitamin C to particles of vitamin C. Now, I'm working with entire vitamin C molecules, so I'm going to call them molecules. Remember that particles is just a catch-all for atoms, formula units, molecules, etc. And you can replace that with whatever you want. If you just called it particles, though, that's fine. For our purposes, anyway. You might need to be more specific in a later class. And those units would cancel it too. And now all I gotta do is fill in the numbers. And I gotta figure out where these relationship numbers are. Whenever you go from grams to moles, where do you get that information? You get it from the periodic table, right? So I would look up the elements for vitamin C, which is right here, C6H8O6. It's on the top of the screen here. And now I calculate the formula mass. Now, obviously, I'm not going to do that by adding things on the periodic table together. We're going to go to LenTech to do that. So let's get LenTech here. Boop, there it is. I've already typed this in. Let me see if I can make this bigger. because I can't read it. I'm sure that you can read it. Now I can read it. It's covering up the chat. Let me just do that. So 1 mole of vitamin C would weigh 176.12 because that's what our formula mass is for vitamin C. So I'm going to write that in there. I've already forgot the number. 176.12. So let's write that down before I forget. 176.12 grams per mole. And that should be a 7. Then the next thing to do is fill in right here for my molecules of vitamin C per mole. How many molecules are in a mole? Well, how many anything is in a mole, right? In 1 mole, there are Avogadro's number of molecules. And now that we've done that, we can punch all of this into the calculator and get the answer. Now, since we have Wolfram Alpha, somebody asked about it. I'm going to just put it on the screen here. So let's capture Wolfram Alpha. Oh, it's already good. I have the wrong part in there. And then you should be able to see what I'm typing, which I can't see because I covered up the calculation. So let's see here. So 0.250 times 6.022 times 10 to the 23. There we go. Divided by 176.12. And when I hit enter, it tells me this is what it interpreted as. So you want to do this times this divided by that. Is that right? And that is right. And so this is the number it gives me. That's, of course, way too many sig figs. So we're only going to keep as many as we need, which would be 3. So when I come back over here, I should write 8.54 times 10 to the 20. So let me get rid of that. And we'll write that on the screen here. So 8.54 times 10 to the 20. And there's our answer. So that's how many molecules of vitamin C are in a 250 milligram tablet. Now, again, we did this problem yesterday, more or less. Like, this is not new for anything that we have done so far. So this is old hat. All right, so now if I do this, there's my answer there. So I got 855. Probably a rounding issue that I did. That's okay. Let me just double check here. Oh, yeah, it's 8548, so I should have put 8.55. So that's fine. If you don't round the last digit, Canvas is set up so that it's fine. Just don't make too many rounding errors. I'm not grading you on rounding. That's not my intent anyway. All right, so that was a basic warm-up problem. Let's do a more involved problem that uses this mole-to-mole concept here. So I'm going to give you caffeine. I'm going to give you 0.10 grams of it. That's a lot of caffeine, by the way. Do not ingest 100 milligrams of caffeine just straight up. Like, your heart might stop. Probably not, but you will definitely feel awake, and then you will feel too awake. Like, you will hear the world vibrating or something. I don't know. In this sample of caffeine, how many grams of it are nitrogen? So now you're going to see that, oh, I have different things that I'm working with in this problem. I don't want to just look at one substance. I want to look at multiple of them. So here's one thing that I'm starting with. And then I want this mass of this other thing. So I'm going to assign my labels here. I'm going to say that label A is my caffeine. And label B is my nitrogen. And so now I can use this chart to direct me where I need to go. Well, I gave a mass of caffeine to start, so I'm going to start here. And I want to get, so I'll just say start. And I want to get a mass of nitrogen, so that means I have to end here. And so what's our blueprint? Well, I'm going to turn grams into moles of caffeine, moles of caffeine into moles of nitrogen, and then moles of nitrogen into grams of nitrogen. All right, we've seen the process in action. Let's go to the... Oops, that's... I opened Final Fantasy V again. It's still open for the break, because otherwise I had to boot it up again, and that will take me some time. Let's see here. So let me capture this. And let's do this problem. So I have caffeine, and I don't want to write out the whole formula, so I'm just going to write caffeine like this. And from our little chart, we said we were doing something like this. So we're going to do grams of caffeine, moles of caffeine, moles of nitrogen, grams of nitrogen. And so we're going to do 3 conversions because we have 1, 2, 3 steps to go through. So let's do that. So the first step, we're going to do grams of caffeine to moles of caffeine. And you can do that. That's easy enough. You just look up the molar mass on Lentech, right? Okay. For the next step, we're going to do moles of caffeine to moles of nitrogen. And this is what we did yesterday at the very end of the lecture. How many moles of nitrogen are in 1 mole of caffeine? Use the formula. We'll do that in a second. Finally, we'll do moles of nitrogen into grams of nitrogen. And that's easy enough because we know what nitrogen is. It's on the periodic table, right? You don't even have to go to Lentech for that. Just look at your periodic table. And then when we're done, our answer should be in grams of nitrogen. So let's go fill in the numbers. How many grams of caffeine are in a mole of caffeine? Well, that's where Lentech comes in. Oops, hold on. Window capture, Lentech. Let's see if this works. Sweet. Okay, I gotta make it bigger though. So we want caffeine, and I don't have it on the screen anymore, so I gotta go over here. So C8, H10, N4O2. And that's what I got, 194.19. So we'll write that in here. 1 mole of caffeine, 194.19 grams of caffeine. All right, that one's easy enough. Now let's do this. How do I go from moles of something to moles of a part of it? Well, we have the formula up there, right? So caffeine was C8, H10, N4O2. So in 1 mole of the big thing, how many moles of the small thing are there? There's 4, right? So in 1 mole of the big thing, there are 4 moles of nitrogen, the small thing that we're looking at. So that's just like what we did yesterday. And then finally, we can turn grams of nitrogen and moles of nitrogen back and forth, because we know in 1 mole there are, whatever it says on the periodic table, grams of nitrogen. I believe that's what it says. I'm just writing down all the numbers. You don't actually need them all. And you're only going to have 2 sig figs anyway from your answer, because of what you started with. So that's fine. All right, let's go punch it all in the calculator. So let's get Lentech back here. Or not Lentech, I'm sorry. Let's get... There we go. I don't know how to... I can do this. There we go. All right, so let's punch in what we have right there in this space. So let's see, 0.10 times 1. I'm going to ignore the 1s. Times 4. I'm just going along the top here. 14.007 divided by 184.19. And let me make sure that that captured right. I got to scroll down. So that's what it interpreted it as, which is what I typed in. And the result it gave me was 0.028852 whatever, right? I only get 2 sig figs, so I'm just going to write 0.029. Now, let's check this answer to see if it makes sense, because this is actually a problem where you can conceptualize your answer, right? If I'm looking at part of my 0.1 grams, I should get a number that's smaller than that, right? Is my answer smaller than the 0.1 grams I started with? It turns out it is. So that's a good check. You can look at your number and say, oh, okay, well, if I'm getting grams of this part, it must be smaller. Likewise, there are other problems where maybe you're doing this in reverse and you're like, oh, this is how much nitrogen was in the caffeine. What sample did I analyze? And you go, well, it has to be bigger than the nitrogen because it contains other stuff, right? So if you're given a problem where you do this Gamolmaga sort of process, you can actually consider the magnitude of your answer. And that gives you a good check to say, okay, if I got a number that was way too large, like 10 to the 22 or something like that, maybe I used the wrong number, or maybe I accidentally multiplied instead of dividing, or something like that. So just be mindful of looking at your answer and going, yeah, that makes sense when you look at what you start with. Sometimes you can't always do that, but in this particular case, you can. All right. Let me know if there's any questions on how to do that, because this isn't an easy skill. This is the hardest thing that we're going to do in this class, I think. And if you can make it here, you can make it anywhere in Chem 140. All right, so you've seen me do it. Now I want you to try and do it. But I'm going to throw a little twist in there. I don't want grams in this case, but I am going to give you a similar problem. I'm going to give you adrenaline. This is the formula for adrenaline, C9H13NO3. This is what we sell in EpiPens. I believe, right? EpiPens are just adrenaline shots, right? I don't actually know that now that I think about it. But anyway, adrenaline, which is a very important biological compound, has this formula. If I give you 0.1 grams of it, 0.10 grams of it, sorry, how many atoms of hydrogen are in the sample? You're going to do more or less the same thing, right? Because this is the substance that you're starting with, and this is its mass, so you're going to start here. But where the heck do you end? Well, if you have atoms of hydrogen as your objective, hydrogen is different than what you started with your compound, so you're going to end here. So how do you do that? Oh, are EpiPens epinephrine? Actually, epinephrine and adrenaline, are they the same thing? I don't know. I don't know common names versus chemical names. Like, I know that adrenaline is important to you, but I think that's obviously a common name. I'm going to have to look this up while you're working on this problem, just because now I'm curious. So go ahead and try this problem here. Tell me how many atoms of hydrogen are present in the sample. Do the calculation. Make sure you're writing out all your units. I'll give you like 5 minutes to work on it, and then I'll come back and check on you while I'm researching epinephrine. See you in a bit. How are we doing? Any questions? Let me know in the chat. All right, one more minute and we'll go over the answers. All right, let's do the calculation here. Let me clear Photoshop real quick before I put it on the screen. All right, so I lost the stylus. There it is. So we have 0.10 grams of adrenaline, which I'm going to abbreviate like that. And our little blueprint that we were figuring out on how to play was we had grams of adrenaline, which we were going to turn into moles of adrenaline. And since I want atoms of hydrogen, I could do this. And then I can do that. So let's do those calculations and conversions here. So the first one, we're going to turn grams into moles. So grams of adrenaline into moles of adrenaline. We'll look that up on Lentech in a second. And then I have moles of adrenaline, moles of hydrogen. And then finally, moles of hydrogen into atoms of hydrogen. And so now I got to look up the numbers. So I got to look up the molar mass of adrenaline. I'm not going to put it on the screen this time. I'm just going to type it in. So, oops, that's the wrong window. C19. That's not what I want. Hold on. C. It's not C19, is it? What even is it? Hold on. C9H13 NO3. And I got 183.20. Let me know if that's wrong. So 1 mole is 183.20. Let me know if that's incorrect. And then for moles of adrenaline and moles of hydrogen, well, if this is the formula, and I have one of these, how many of the little thing do I have? Well, in 1 mole of adrenaline, there are 13 moles of hydrogen, because that's the formula. And then finally, in a mole of anything, there are Avogadro's number. Atoms in that thing. All right, I'm going to punch it in my calculator here. I'm going to do this on my graphing calculator just because I have it in my hand already. And I got 4.28 times 10 to the 21. Oh, 4.27 actually. Well, it doesn't really matter. Either of those answers is fine. All right, there you go. That's how you do these types of problems. So now that you've seen these two problems, you've basically seen every permutation of them. So if you can do these two problems, you're all set. Oh, now that I've flipped back over to here and I saw this, I noticed that, like, oh, there's only 2 sig figs here. So my answer should only have 2 sig figs. So it should be 4.3 times 10 to the 21. I wrote too many digits. That's too bad. All right. I'm going to give you these for your practice to do right now. So you're going to start with the same sample of iron 2 iodide here. And this is how much I'm giving you. And so what I want you to do is answer these 4 questions. And you're going to notice that the same first step or so in your calculation is going to be used over and over and over and over again in your calculations. That's by design. You're doing it correctly. Once you get to moles of FeI2, then you're going to change what you do from there based on what the problem is asking you. So here are a bunch of different permutations for you to try. Go ahead and do these. We'll go over the answers in about 6 or 7 minutes or so. And then we will, once we've done that, we'll take our break and then we'll pull up the lab because I think this is the last slide. I'm going to just check that real quick. Yeah, this is the last slide. Okay. Go ahead and do these, and I'll check back in you in just a little bit. See you soon. How are we doing? Let me know. If you get any answers at all, go ahead and put them in the chat just so that other students can compare them. Let's do 2 or 3 more minutes, and then we'll go over the answers here. And then we'll take our break. All right, let's go over the answers here. So let's go to this. Oops, I didn't clear that. All right, I'll leave those first two on the board here. So a sample of iron 2 iodide has a mass of 0.522 grams. All right, and for this first problem, we want to know how many particles there are. So we would do something like grams to moles. And then we could do moles to particles. So in this case, it would be formula units FeI2, because it's an ionic compound. So we'll just do that. So grams to moles. We'll cancel that out. And then we'll do moles to formula units. I'm just going to do funits, I guess we'll say. I would abbreviate it F.U, but that seems vulgar. All right, and now we got to look up the molar mass on Lentex. So FeI2. I got 309.65 grams per mole. And in a mole of anything, there are Avogadro's number of that thing. And so we can now type that in the calculator. And what do I get? 0.522 Avogadro 309.65. I got 1.02 times 10 to the 21 formula units, or funits, of FeI2. There we go. Now for the second one, we're going to do moles of iodine. And you're going to notice that this part right here, we're just going to be reusing that over and over and over again. Because to get from grams of FeI2 to moles of FeI2, we just need to do that as the first step. Then we do moles of iodine. And then that's our answer, right? So what I'm going to do is I'm going to do this. I'm just going to copy and paste everything that is the same. Copy, paste. Whoop. And we'll just reuse it. And so now we just have to fill in how many moles of I are there per FeI2. Well, we know that there's a 2 right here, so we'll just do that. Boop. There you go. And so that's how many moles there should be. And I got 0.00337. Now, I'm going to skip the third problem for now because the fourth problem just asks us for how many particles of I there are. And if I know the number of moles of iodine, then really all I have to do is take this number and turn it from moles to particles. Now it's iodine. I should probably write ions, but that's okay. There we go. Now we know how many atoms there are in the sample. So in 1 mole, there are Avogadro's number. You could repeat the whole calculation, but you're going to get the same answer anyway, so you might as well just take the number. Work smarter, not harder, yeah? There you have it. And then for the last problem, if we go back up to our chart here, instead of going to moles of iodine, I could instead go moles of iron and then grams of iron, right? And that's like the problem that we did earlier today with the, I want to say it was vitamin C and nitrogen. So we could do that. So we'll just copy and paste the stuff that we started with. So there it is again. I'm actually going to move this a little closer. There we go. That's the wrong color. There we go. Mole, Fe. And so now all of our units will cancel out to give us grams of iron. How many iron are there in the formula? Well, there's 1, so you just do this. And you might think, well, that's not really helpful. But you have to do that step in order to have the units cancel out. And then when you go over here, we just look up iron on the periodic table. 55.845. And what do we get for our answer here? Divided by 309.65. And I got 0.0941. All right. There you go. So that's all 4 problems. You are now proficient in doing mole calculations. And that's going to be helpful for us on the lab that we're going to do in just a second. So first, let's go back here so that you can have your hooray. Hooray. All right. So we're going to take a break. When we come back, we're going to talk about the lab. I'll get that all set up during the break. So let's see here. Oh, oops, that was from... I was working on something yesterday. Why can't I do that? Oh, there we go. So do that, and then that, and there we go. So we'll start the timer. I'll get the music back up for Final Fantasy V here, and I'll see you in a bit. Oops, I hit too many buttons there. Oh no, I have nothing. Yeah, here's what you can see what I'm doing here. Well, this is way too big, but I don't know how this is actually going to show up. There you go. Like I'm moving the cursor around. That's what that sound is. So I haven't gotten very far. Let's see here. Yeah, I'm level 4, so I haven't gotten very far into the game. But if you haven't played Final Fantasy V because you were born after, like, 99 or something, like, it's fantastic. Like, absolutely play this. The music is just beautiful. How do I exit the game? There we go. That's what I want. Okay. This will go away now. Okay, so what am I capturing now? Now I'm capturing... where is it? I had this all set up, and then now I can't find it. Oh, there it is, right there. Alright, just ignore that it says blueprint at the top. Wait a second, this is not the right window. That's weird, hold on. I'm like moving something on my screen, but it's not actually working. There we go. I don't know why. Bizarre. Okay. Okay, so we're going to look at lab number 4 today. So, lab number 4 is... Oh, this is no good. Hold on. Lab number 4 deals with molar ratios. What does that mean? Well, it has to actually download. Why is it not downloading? I mean, I'll just download it manually. Actually, why would I download it? I'm the publisher of all of these files. Let me just find it on my flash drive. Technology isn't working today, I guess. Labs. Lab worksheet 4. Okay. Let me get rid of this for now. And we'll capture instead this one. All right, so the way that lab number 4 works is that you're going to be given what's called a hydrate. And a hydrate is just an ionic compound that also has water in it. You can think of this, I'm trying to think of common examples of hydrates, and the thing that I'm thinking of, but you might not be aware of what it is if you've heard of what is called a desiccant. Inside the little tiny, like, packet that says, like, silica, don't eat, or whatever, the purpose of that is to absorb water. And what that does is it's an ionic compound that can bond water molecules to it. The water just kind of sneaks into the lattice, and it makes a new lattice, and it has different properties. Some ionic compounds can do this because water is abundant. And so, if water is everywhere, new things can form. A really common example of this is copper sulfate. If you have it dehydrated, it's very, very pale blue, almost white. But if you add water to it or allow it to come into contact with water vapor, it turns this deep, deep, deep blue. It's real blue. You may have heard of the term blue vitriol. We did a lot of experiments with it in elementary school when I was a kid, because I guess it was cheap and abundant. I don't know. Anyway, the point is you're going to be working with hydrates here. And actually, let me get to the... let me go over here. Oops, I'm on a new layer, aren't I? Hold on. Merge layers, delete everything. Boop. Okay. So, what a hydrate is is a compound that is like this. So you have your ionic compound. And then you write a big dot. And then you have a number H2O. So an example might be, for example, copper sulfate with 5 water. And so what that means is that for every 1 copper sulfate you also have 5 waters attached to it. Or in other words, 1 mole Cu, oops, I didn't capitalize the C there for some reason. In 1 mole of copper sulfate, there would be 5 moles of water if this was an ionic compound that forms. I think it does. I'm just making up a number, maybe. I don't know. And so you have a molar ratio. And the ratio is 1 to 5. And you get that from this number. Normally, we'd be picking like subscripts, right? But because we're looking at water, we're just doing a different application of it. So if you know the number of moles of this, and you know the number of moles of this, you can make a ratio, right? So for instance, if I had 0.2 moles of copper sulfate and I had 1.0 moles of water, I could find the ratio between these. And the way that I would do that is I would do this. I would take the ratio of water to copper sulfate. So really, the gist of what this lab is going to be is you're going to figure out whatever moles you have of your substances. And then you do this division. Divide the water by the ionic compound. And whatever whole number you get is the ratio. You should get a whole number. If you don't get a whole number, you've probably made a math error somewhere. Now, let's talk about conceptually how this is done. I don't have any space. I need to hit clear here. In the laboratory, what you would be doing is you would be weighing out a sample of your ionic compound. I'm going to call the ionic compound, I'm going to call it X. So this is X dot N H2O. And our goal is to solve for N. And so what you would need to do in order to do that is you do the process that we just described, right? So you need to know the moles of this thing that you have, and you need to know the moles of H2O that you have, so that you can do that, right? Because that will tell you the number. It's the ratio. Okay, how do you do this practically, though? Okay, so I'm going to weigh out. This is my crucible. My crucible is just a sort of ceramic container. And inside, I'm going to fill it with X. More importantly, this is the X with the hydrate. And then what I'm going to do is I'm going to heat it up. So I'm going to have like a little ring stand here. And it's attached to a little clamp with a sort of like holdy doodle thing. And so there's my crucible. And so inside there would be my hydrate. And then what I'm going to do is I'm going to put a Bunsen burner under it. And you've seen a Bunsen burner. You saw this in the previous lab. I don't want to bother choosing another color, so we're going to heat it up with a purple flame here. Blue flames are good, but purple flames are real hot. And now the act of doing this causes the H2O to escape because you boil off the water. And so the hydrate becomes an anhydrous compound. And then finally, when you're done in your crucible, I'm trying to indicate that this is different than what it was before somehow, is the anhydrous compound, which is just X. So your H2O is here. Well, how the heck do you figure out the moles of water if you've boiled them away? They're gone, right? Well, it's easy. If you know what the mass of this is... Oops. And you know what the mass of this is... Well, we'll just subtract them, right? And then this will go away. So if you know the mass before and after, you do the heating, you just subtract. Whatever the difference is, must be the water that escaped, right? Once you know the mass of the water, you know the moles of water. And if you know the mass of this, because you weighed it, you also know the number of moles of this. And once you know these two numbers, you can make the ratio. So your lab is going to involve doing the calculations that we did today and yesterday, but a little bit easier, actually, because really all you're doing is turning a few things from grams into moles. It's the moles that are important. In specific arrangements, could one consider salt a hydrate? Sure. If you put salt in a really moist or humid area, it tends to like clump up. You can get a salt hydrate there. Typically speaking, though, we wouldn't want to like have our salt be hydrated because then it's not as the texture is all weird, and it's also harder to like apply to say like your recipe. So like if you go to the salt shaker and you try and shake the salt onto your food and it comes out in these giant blobs, that might be a lot of salt. So anyway, that's the gist of what we're going to do in the lab. And let me get the document up on the screen here. So what you're going to do is you're going to watch a video that's linked in the lab. And it's basically going to be showing you this process that I drew out on paper for copper sulfate. And so you're going to see that it's very blue when they start, and that when it's done, it's very gray. And there's going to be numbers in that you're going to have to record. So that's going to be table 7 right here, which is sort of on the screen. So table 7 is going to be from the video. Table 6, on the other hand, I have done the experiment for you. And so you can see here in the data table that here's what the crucible weighs by itself. This is just the container. Here is the crucible and the hydrated sample. So this is after I put X.NH2O inside, where that compound was this up here. What is the mass of the sample? Well, how would you get that? Well, if I... Oops, I'm going to have to clear all this. Oops, that's not what I meant to scroll. If I weigh the mass of the crucible and I report its mass to some amount, so whatever it ends up being, and then I put stuff in it, and then I again do the subtraction, so whatever these numbers are, these would just get subtracted out. whatever the remainder is the ionic compound and the hydrate that's inside. So, by subtracting the number in row 2 and the number in row 1, I can get the number in row 3. And then down at the bottom in row 4, I have heated the sample, and this is what it weighed after I got rid of all the water. So, what 2 numbers would I subtract there? If you aren't sure, do this sort of analysis. Write out what's in your container for those rows and see what happens when you subtract them. Just cross out things that are in both cases, because if you subtract, it's the same thing being removed, right? And whatever is left over is the result of that subtraction. And if that number is what helps you, then you can put it in the data table wherever you need to. For the top part of the table, above the line, you should be able to calculate all of those numbers from the data. So you don't have to do any calculations other than addition or subtraction for 1 through 6 up here. Oops, hold on. I don't know where my cursor is. I'm way down there. Okay. Up here. So there we go. I'm cheating. So 1 through 6 only require addition or subtraction. And you can't see that because I'm a little off. There we go. Down here, for the rest of these, you might need to convert mass to moles, depending on what it is asking. But you know how to do that, right? How do you figure out the molar mass of your compound? Well, remember, it says what you're working with up here at the top for example 6. For example 7 down here, you can see that I've given you a different formula. So make sure you look up the formula that you're using for the experiment, because it changes for each part. And then go type it into Lentech. And then do the calculation that's asked for. So for example, in number 8 here, moles of anhydrous compound remaining, the anhydrous compound would just be this, FeCl3. And you know what its mass is because you have that in box number 5 right here. So you could turn number 5's mass, assuming it's this, into moles using the Lentech number. And then you'd enter that right here in box 8. Then you would just need the moles of water. Well, you know what water is. It's H2O. You can look up its molar mass on Lentech, right? It's about 18 or something. You know the mass of water, so you can turn the mass of water into moles and put that here. And then you just make your ratio, just like we've shown. Now, I don't want to do any examples specifically of these types of problems because I don't want to use these numbers. So I'm going to make up an example here. But in order for me to make up an example, I have to actually go look up a number really quickly. So give me a second. It's going to take me a sec to just make this problem. So I'm going to say that we're going to use calcium carbonate dot XH2O. And so the mass of calcium carbonate that we're going to use is going to be, and so give me just a second. I need to type numbers in my calculator so that this works. Okay, so let's say that I have this. So I have that many grams of water. And I have just a second. Making problems is hard. I'm gonna have to actually sit down and like prepare one of these. Oh, you know what we could do though? Hold on. I bet we have one in the worksheets. Worksheets online. There we go. Oh, do we not have one like that? Hold on. I wanted to do an example, and now I can't think of one. Hold on. Let me do. I can come up with something. I'm just gonna have to like put that on the screen so that you don't see my scratch notes here. So. So I want this. And then that. There we go. I got it. Okay. Okay. So 1,000 gram. Okay. Sorry about that. Sorry. I'm trying to make up a problem really quickly, and it's okay. Let's suppose that you got this, and this is your hydrate, and you want to figure out. You want to figure out what N is. So we would have to first convert each of these to moles. So let's do that. So there you go. And according to Lentech, calcium carbonate is actually really close to 100. So 100.09 grams per mole. So how many moles are in here? It'd be 1 over 100, right? 1 divided by 100.09. And so I get 9,991. And now I can do the same thing for water. And we'll turn that into moles too. So 1 mole, according to Lentech, is 18.02. When I do that, I get this. So now we can take those numbers and we can make the ratio. So moles H2O divided by moles of our anhydrous. And so that would be 0.04001 over 0.009991. And when I do this, I should get 4, because that's what I was trying to do. 4.005. Which will make an integer. When you're doing this process, at the end, it's going to say report the number that you get. That'd be this. And then report your number as an integer. Because remember that formulas have to be integers. can't have a fractional formula. Like, you can't have 2.5 waters. That doesn't really make sense, right? You can't cut a water in half. Later on in higher level inorganic classes, you'll learn that you can get fractional things because maybe you have one water molecule that bridges between two formula units. But I'm not going to give you examples that do that. So you're going to just see whole numbers. So if this was the compound that you got and those are the masses that you got, this would be the math that you would do to determine the integer value that goes in the spot up here for n. So we would replace this with a 4. And then there's my notes up above. I was just quickly scribbling something out to try and solve the problem. All right. That's all I got. That's what I have for your lab. I don't know if people had questions for other stuff. We have like 15 minutes left if you want to do any other like sort of exercises or you have questions that you'd like me to go over. Go ahead and put them in the chat. I put the music back on for Final Fantasy V. I already closed the application. So I'm just going to hit mute. I'm going to go use the restroom real quick. And if there's any questions, I'll answer them when I get back. So I'll see you in just a moment. All right, I'm back. I realize that's not much time to post any questions, but if anybody needs anything, like, let me know. I see people are starting to duck out because I can see how many people are in the stream right now, and I assume that when that happens, people are like, "Okay, I'm done. I've got everything I need to." Well, I'm going to be around all day anyway. I'm doing something from like 5 to 7 tonight, but afterwards, like if you have any questions, you can put it in the Discord or send an email. I'm going to upload your grades for the lab number 3 tonight, I think. I have them all done. I finished it yesterday, but I have to go actually put your scores into a spreadsheet, which I then put on Canvas. So like I'm like 99% done. The grading part's done. It's just like 15, 20 minutes more work for me. So I'll get those back to you tonight. But yeah, if there aren't any other questions, I guess we're all done here. So thanks for coming out to the Wednesday lecture. I hate that we have to like have these extra lectures because the content stretches on long. I'd rather kind of go slow and give you time to do these exercises though, because this really is the meat and potatoes here of the class. And rather than rush through it all at the end, we have enough time that like I can slow down and just let you guys do all of the examples. So that's what we're doing. Next week's week 9. We're gonna do units 13 and 14 probably. 13 is real short. We've already done unit 13 basically. It's basically what you're doing in the lab. And then I want to say 14 is balancing equations or 15, one or the other. So those topics will be relatively light. And then 15 and 16 are just applications of what we've been doing. So you've seen like 95% of all of the content that I'm going to teach you in this class already. The YouTube for the lab video says it's unavailable. Let me address that. Let's see if I can find that. That's terrible. Okay. Yeah, I was using that video. Okay, that's going to be an issue. Hey, guess what? I need to update that so I can find a new lab. I might actually have to go back to the campus and record something. Great. Okay. I really appreciate you letting me know that. I will figure that out. I will figure something out about that later this week because I may have to move the lab back a week because of that. So I will try and find another video and see what I can do. Yeah, I don't know what else to say. I will go and figure something out for that. Otherwise, until then, make sure you get quiz number 6 done. It's due tonight. Have a good one, and I'll see you next week. Take care.